Good morning.
Good morning. Good morning.
Good morning.
Good morning. Good morning. How's everybody doing?
I'm happy I'm not at work.
That's a good thing. That's a good thing. Get a break. I was 2 seconds from canceling class. I was tired. I wanted to stay in the bed.
Don't we all? Oh my goodness. I work at Starbucks, so I make sure I get up super early and make sure everybody gets to work.
hmm
So I'm always so tired handing people their coffee. It's so funny.
Oh man.
They're like, why don't you get some more coffee? I'm like, oh gosh.
Let's see. I think everybody's in. Is everybody in? Okay, cool, cool. So good morning, everyone. If you just still see one or two people still getting connected with the audio, but good morning, everyone. Hope all is well. Hope everybody's ready to get this weekend started right. It's Thursday. So as soon as we close out today, that'll be it for our week. So we'll talk about a couple sections and then call it a day, call it a class. We last class we just reviewed if anybody missed it. And so I mentioned 7.1's definitions, those have been posted. Hopefully you saw the email, let you know that I did post those. Also your homework and homework for 7.1, because all it is just definitions. And then your test, that's been posted as well. So, as soon as you guys get a chance to get ready for it, be able to, go ahead and get in there and knock it out. I posted a review for it as well. So, yeah, we should be set up to go ahead and, make that happen. But of course, if you have any questions, always feel free to ask. And we'll go from there. So, trying to look and see if I want to write that. Okay. So 7.2 has a lot of terms as well, but it has some calculations, so we'll get to it. Where's my green? I'm just writing a note to myself on this. All right, so we're starting with 7.2, measuring the quality of a survey. Okay, I thought so. Let me see if I can change these screens. Okay. All right, so just trying to point out just different things in here before we actually get to the actual calculation. Certain things that you may be asked in my math lab, so I'm trying to streamline what I write. But one of the points that they made was statisticians evaluate the method used for a survey, not the outcome of a single survey, and that's because of biases. You know, those things will let you know the validity of the actual survey itself. So they actually, evaluate the method used first before you look at the outcome. All right. All right, so one of the first major points they point out, statistics vary from sample to sample. So no matter how many different samples we take, the value of P is your population proportion, is always the same because you have your population, your large body. In other words, you have a statistic on the United States, everybody in the United States. Then when you take a sample out of everybody in the United States, let's say if you take 10 people, a sample of 10 people, and you just go around taking a sample of 10 people, that statistic could change for your sample according to who you chosen each time you choose, because you're choosing 10 different people each time. So you don't know what you're going to get. So let's say, for an example, they use and I meant to write right here. That's p hat. That's how you say it, p hat. Oh, if I just emphasized. I know I said it, but I didn't emphasize it. But that's p hat. All right. So all right. So if you had an example that 25% of the population are cat people, in other words, people who love cats. Let's say for your first time you run your sample, that population parameter doesn't change. The population will always be 25% of the population are cat people. And then when you take your sample and you evaluate your sample, do your survey on your sample, you may come to find out that 25% of your sample are cat people. Then if you run the repetition again, once again, the population parameter is still going to be 25%. But then the next time you take your sample, because now you're choosing a different set of people, a different sample, 50% of those people could be cat people, but the population parameter doesn't change. And then the third time you do the same survey, once again, population is the same. But then out of this sample, none of them could have been cat people. Just so happened that you chose, let's say if you chose 10 people, just so happened that the 10 people you chose, none of them like cats. So that's what we mean by the population parameter will stay the same, but your sample will vary from sample to sample. Your parameter populate or sample proportion will vary from sample to sample. All right.
So there is no rule that said like the total of the sample should be 100, because here it's just 75, right?
Now when you say what should be 100 or what could be 100?
Like it's just the total of the repetition of the samples, like first time,
Oh.
second, and third.
Well, see, now when you look at this right here, well, let's go back here for the population parameter, since that doesn't change. 25% of the people of the population are cat people. 75% of the population are not cat people. You know what I mean? So then when you go to your, if that's what you're talking about as far as your 100%. Now, if you go to your sample is a different entity by itself. So you got 10 people over here, 25% of your 10 people are cat people, 75% are not. But then when you take this is a different sample size, so it's 50-50.
Okay.
And then this is a different sample, not different sample size, but a different sample. And then out of this sample, 0% are cat people and 100% are not cat people. You know what I mean? So each sample is different, have a different set of 100%. You see what I mean?
Yeah, sure. Okay. Thank you.
Mm-hmm. All right. All right. So just want to point that out. Probability distribution of p hat has a special name, and it's called the sampling distribution. And it is a statistic we use to estimate a population parameter. All right, so make sure I'm here. Okay. Bias is measured using the center of the sampling distribution. It is the distance between the center and the population value. Precision is measured using the standard deviation of the sampling distribution, which is called the standard error. I think you got that. Yep, standard error. SE for short. So when the standard error is small, we say that the estimator is precise. Hold on, let me check something real quick. Trying to stay consistent. I use purple. Okay. Yeah, go back. All right, so this is 2. Oh, no, it does not affect. All right, so the next major point that they have in here is that the size of the population does not affect precision. So precision is an estimate, a precision of an estimator does not depend on the size of the population. It depends only on the sample size. So remember, we're using the sample to predict the population. So the sample size is what we're leaning on, not necessarily the population size. So an estimator based on a sample size of 10 is just as precise I can just write a million. So an estimator based on a sample size of 10 is just as precise in a population of 1,000 people as in a population of 1 million. Because once again, we're basing it on the sample size. So a sample size of 10 is a sample size of 10, no matter what population you pull it from. So now if you want to increase your accuracy, then you probably would up your sample size, increase your sample size. But if your sample size stays the same, the precision of it is going to stay the same. All right, any problems? Everybody good? So next one. I'll go again. What do I want to say? I want to say understand. Hold on, I want a better word from that. Shoot. Mm. I want to say again. I'm trying to think of a good word to write. What we should know. Yeah, I don't know. All right, so trying to look for a better word, but I guess that's good enough. What we should know from the sample size of 100 people, just an example that they have in the book, that the estimator p hat is unbiased for all sample sizes. So that's as long as we take a random sample. The precision improves as the sample size gets larger, and the shape and the shape of the sampling distribution is more symmetric for larger sample sizes. Surveys based on larger sample sizes have smaller SE standard error and therefore better precision. All right, so we get to the calculation part. All right, so finding the bias and standard error. Bias and standard error are easy to find for a sample proportion under certain conditions. So the bias of p hat is going to be 0, and the standard error is this formula right here. SC is equal to the square root of p times 1 minus p over n. If all right, so two conditions. The sample must be randomly selected from the population of interest. That should be either. I just said ETH. So either with or without replacement. And then condition 2, if the sampling is without replacement, the population must be much larger than the sample size, at least 10 times bigger is a good rule of thumb. All right, so in pet world, suppose that there's a population of 1,000 people and 25% of the population are cat people. Cat people love cats but hate dogs. We are planning a survey in which we take a random sample of 100 people without replacement. All right, so what value should we expect for our sample proportion? What's the standard error? And how do we interpret these values? So I should put what's the fact? I'm gonna make this. All right, so let's look at A. What should, excuse me, what value should we expect for our sample proportion? See, don't say if it's unbiased. Okay, let's just say. All right, so A was what value should we expect for our sample proportion? So the sample proportion is unbiased, so we expect it to be, I say respect is, we expect it to be 25% cat people, same as the population. All right, the standard error. So we go off the formula, which is P times 1 minus P over N. So population proportion is 25 or 0.25 when you convert it to a decimal. So that's 1 minus 0.25 all over. Lowercase n is your sample size, which is 100 for us. Capital N is always your population size. Lowercase n is your sample size. Um, all right, so that's just walking through the steps. If you didn't have most calculators now, you can just put it in just like this and would have gotten the answer out. But if you have like a regular 4-function calculator, that would just be the steps walking through it, in the order that you would do it and all the good stuff like that. So bottom line, it calculates the 0.0433 as our standard error, or as a percentage, moves your decimal 2 places to the right. That would be 4.33%. All right. Yeah.
It's the new one. Have you seen it? I'll show you in a sec.
Was that's not for me, right? Whoever unmuted.
Well, it might be on Instagram. So I need to get
Is it
Instagram.
this knife?
Hold on one
Is it
second.
this?
It's the
Go. I think that was by accident. That was done, so it'll be all right. So interpretation, if we take a sample size of 100 people, then we expect 25% of them to be cat people, give or take 4.3%. So that's what that means for us. All right, any questions on what that means before we go to the next thing? Looking at something real quick. Okay. All right, let's see. We have in this section left 7.3 and 7.4. No, 7. Guess what? We can do 7.3. So the central limit theorem, CLT for short, it tells us that if some basic conditions are met, then the sampling distribution of the sample proportion is close to the normal distribution. And don't forget, this is our normal distribution shape that goes back to our z-scores. So let's say something in chat. All right, not a problem at all. Thanks for letting me know. Appreciate it. I do appreciate it. All right. All right, so those conditions, we have seen 2 already, but then they add another one. You know, we saw 2 in our last section, but then they add another one. Not sample size. Well, it should say sample is collected, not sample size. Sample is collected at random. So samples are. Sorry about that. All right, so the conditions, first one is random and independent. So your samples are collected at random and are independent of each other. We're looking at a large sample size. So we want our sample size to be large enough to have at least 10 successes and 10 failures. And we need a big population. All right, so then we're looking at a big population. If the sample is collected without replacement, then the population must be at least 10 times bigger than the sample size. Okay. All right, central limit theorem tells us that if our conditions are met, then the sampling distribution or sample distribution of p hat is approximately, that's what AVP is approximately. And they gave us this right here in the book. Capital N, P comma, square root of P times 1 minus P over N. But we know that square root of P times 1 minus P over N is our standard error. And so this notation, though, if you remember from the last time that we saw it, means that if I have normal distribution, that's what the capital N stands for, and this with the parentheses, the first letter or that first component of what's in the parentheses is our mean. So this is saying that our population proportion will be our mean, and then our standard error will be our standard deviation. So they just gave the notation right here, but I just wanted to make sure we're making the connection into what they're trying to say. All right. Okay. This says if you don't know the value of P, which is your population proportion, then you can substitute the value of P hat to calculate the estimated standard error. All right. Any questions on what I've written so far? And what time is it? 10:23.
I have a question.
Yes.
Can you go back to the equation and just tell me what those the letters mean? You said capital N means something.
Oh, that means that, we're talking about being normally distributed. Right here, when we talk about normal distribution, that goes back to chapter 6. That means normal distribution. So whenever you see that notation, the first letter is your mean, and then the second letter is your standard deviation. So that comes from 6.2. You first introduce that. Yep, 6.2. So check your notes for 6.2. That's where we first, initiated that. So that's where we're making that connection from. All right, was that the only one?
Mm-hmm.
Okay. All right. Anything else? Anything else? So what we're doing is we're setting ourselves up. So for next class, when we actually get into the example, we're going to be able to go to z-scores. And so we're making a connection to z-scores. So that's why we wanted to be normally distributed. All right. Anything else? Anything else? Everybody good? Everybody straight? Okay. So next class, we're actually going to get into examples when we talk about calculations. In 7.3, I just wanted to set us up so we can get that out of the way. And we'll do some actual examples out of 7.3, then we'll do 7.4, and then we'll be done with chapter 7. All right. So any questions before we close out today? Anybody?
No, thank you.
All right. Sounds good. Sounds good.
Have a
So
wonderful day.
thanks. You do the same. You guys take care. Don't forget there's a storm coming. So make sure you prep and be safe. Have a great weekend. And I will see you on Tuesday.
Thank you. See you then.
Thanks. Take
Good.
care. Mhm.